Hi, Dr. P here, and in this lecture video we'll take a look at ionic bonds and the strength of ionic bonds. Now, what do ionic bonds look like? Well, your typical ionic bond will have a nonmetal anion and a metal cation. And the anion will typically have the electron configuration of the nearest noble gas, and the metal cation will have an electron configuration of the previous noble gas. That is to say, they'll have all of a particular energy level full. We'll say that their valence electrons are full. So if I had F as my my anion, F minus, it would look like neon. If I had lithium plus, it would look like the previous noble gas, which is helium. If I had sodium chloride, my chloride would be Cl minus, it would look like argon. My sodium would be Na plus, and it would look like neon. So we say that one element, the cation, the metal, donates an electron to the anion, or possibly more than one electron. Now, how do we figure out how many electrons? Well, we'll simply use the periodic table and we'll count over. So sodium has one electron to give up, so it'll be Na plus. Magnesium has two. 1, 2. So it would be Mg2 plus. Scandium has 3, for example, Sc3 plus. Aluminum has 3. 1, 2, 3. Oxygen, you have to add 2. 1, 2, so it would be a 2 minus charge. Nitrogen, you have to add 3. 1, 2, 3. So it would be a 3 minus charge. The halogens are all just adding 1 electron, so they're all minus charge. When you get to carbon, you could go either way. Carbon's kind of weird, and it tends not to form ionic bonds, but rather covalent bonds, and we'll look at that in a future video. All right, so let's put the periodic table away for now, and take a look at we'll take a look at the stability of ionic solids. We have to think about the size of ions, and it's kind of difficult to measure the size of ions exactly. Just like measuring the size of a neutral atom is very, very difficult. So factors that affect ion size include the parent atom size, and then removing electrons will make a smaller ion, because we're taking electrons away, so we won't have the highest energy electrons that are the furthest from the nucleus. Adding electrons will make a larger ion, but when we have atoms that have the same electron configuration, we call those isoelectronic. the size tends to decrease as the nuclear charge increases because we've got fewer electrons relative to the nuclear charge. But don't bother writing that down. Just remember these trends here. Okay, so question is, how strong are ionic bonds? And the answer is it depends. So if we have a soluble ion in a solution, it's not very strong. Okay, ionic bonds can be very strong. On the order of 1,000 kilocalories per mole, which would be like 4,000 kilojoules per mole for certain ionic bonds. So this is about 4,000 kilojoules per mole. But can be easily broken in aqueous solution in many cases. Okay, so that's for soluble stuff. So soluble salts. So something like magnesium oxide may have a bond energy of 1,000 kcals per mole, kilocalories per mole, 4,000 kilojoules per mole, and that isn't soluble. But maybe something like, well, we'll see in just a minute, lithium fluoride has a bond energy of around minus 600 kilojoules per mole. So that's about minus 150 kcals per mole. And it is soluble. We'll see in a later lecture that ionic covalent bonds may have bond energies of around 400, 500 kilojoules per mole, but they don't break when you put them in aqueous solution. So the it depends is something to really think about. Ionic bonds can be very, very strong, but they can also be easily broken in aqueous solution. Like magnesium chloride will have strong bonds, 1,000 or more kilojoules per mole, and yet magnesium chloride is soluble. So you can't always tell based on the strength of the ionic bond whether or not it's soluble or not. There are other factors going on. So let's take a look then at how we quantify ionic bond strength. So what I'm going to introduce to you is something called a lattice energy. And the lattice energy is the change in energy that takes place when separated gaseous ions are packed together to form an ionic solid. Okay, so delta E for separated gaseous ions to form an ionic solid. Okay, and we can't directly measure this, but we can get at it. And we'll get at it by using Hess's law. So in general, we would have M plus, which is a gas, plus X minus, which is a gas, and that goes to Mx, which is a solid. So we have our metal and we have our non-metal M and our non-metal X. And maybe it's M2 plus and we've got 2X minus, or we have X2 minus. The exact charges depend on the case. So let's look at, as an example, solid lithium plus half a mole of gaseous fluorine, and those will react to give lithium fluoride solid. Now what we're going to do is we're going to use Hess's law. And so we'll start with, draw this here, energy. Let me scoot this up just a little bit here. And so we'll start with solid lithium plus half the gaseous F2. So first we'll have LiS is going to Li gas, lithium gas. And that has a delta H of 161 kilojoules per mole. So let's draw in 161 here. That's about 161. That brings us up to here. And so now I've got Li gas plus 1/2 F2 gas. Well, now I need to ionize my lithium. So that's lithium gas goes to Li plus gas plus E minus, and delta H here equals 520 kilojoules per mole. Okay, so that's a bigger jump up here. These are not drawn to scale. This is 1, 2, and then in my third step here, I'm going to split up my half a mole of F2 into just 1 mole of F. So 1/2 F2 gas goes to F gas, and delta H equals, and this is 77 kilojoules per mole. So up here I've got my Li plus gas plus 1/2 F2 gas, and then it hops up just a little bit here, so this is number 3, Li plus gas plus F gas, and then for number 4 we need to have our F gas picking up an electron plus E minus gives us F minus gas. And here my delta H is actually negative. It's minus 328 kilojoules per mole. So we'll drop down to maybe about there. So this is Li plus gas plus F minus gas. Now way down at the bottom here we have LiF solid. And we can actually calculate the energy here, and this would be our bond energy, if you will, and this happens to be minus 617 kilojoules per mole. So that's for our overall reaction. So overall, Li solid plus 1/2 F2 gas goes to LiF solid, delta H equals minus 617 kilojoules per mole. So my last step here is these two guys combining. And it's this type of reaction here. So it's Li plus gas plus F minus gas react to give LiF solid. And now my delta H here, I could call these delta H 1, 2, 3, 4, oops, 4. Delta H5 equals, we could calculate this using Hess's law, using these four and our overall, and calculate what this one had to be. And what we get is minus 1,047 kilojoules per mole. So reaction 5 here has a delta H of minus 1,047 kilojoules per mole. So we can see what are our two biggest delta H's here. We have our overall delta H going from solid lithium and half a mole of gaseous fluorine to lithium fluoride solid, and that's minus 617. Well, if we went from a gaseous lithium ion and a gaseous fluoride ion, we would have a delta H of minus 1047. So really, this lattice energy, this is our lattice energy. This lattice energy is what gives us the bulk of, or accounts for most of, the overall delta H. It accounts for most of the bond strength, if you will, of ionic bonds. All right, so I know I went through quite a bit here. Don't worry too much about recreating this diagram. I just want you to understand it. And yeah, we will go from there. So in the next lecture video, we'll go ahead and we'll take a look at covalent bonds and the strength of covalent bonds, and then we'll focus even more on covalent bonds in terms of details and how we represent them when we draw them. All right, so until next time, stay safe out there. Bye now.